Welcome back to the Neural Intel podcast. I am absolutely thrilled you're tuning in today because we are about to unpack something that has effectively set the internet well, a very specific part of the hardware market, at least completely on fire over the last few weeks.
It really has. I mean, it is rare that we see this level of disruption in such a short window of time, specifically where a software release entirely dictates a consumer hardware buying frenzy.
Exactly. Let's dive into today's topic. We are looking at OpenClaw. If you have been on GitHub or scrolling through X in the last month, you've seen the charts. You've seen the screenshots of Mac Minis stacked up in closets, people building these little ad hoc server farms in their laundry rooms.
Yeah.
But we aren't just here to look at the hype. As always, the focus remains strictly on technical details and the implications of the technology.
Right. We really need to move past the whole, wow, look at the star count factor and look at the how, the why, and the actual architecture beneath it.
Yeah, before we get the ball rolling, though, a quick call to action. If you want to see the diagrams we're talking about today or get the code snippets for the config files we mentioned, and we are going to get into some specific configs, visit the blog at neuralintel.org. We post deep technical breakdowns on AI and ML updates there constantly. Also, please subscribe on YouTube, Apple Podcasts, and Spotify. It really helps us out.
And we genuinely want to hear from you. The comment section is where the real peer review happens, honestly.
We do. We encourage listeners to leave their technical takes in comment section below. Did you try the Docker setup? Did you go with the M4 Mac Mini? Tell us your specs. We want to know if you survived the installation process.
We read them all, and I'm particularly interested to see how many people actually got the permission sets right on the first try.
Okay, let's unpack this. The subject is OpenClaw, formerly known as Clawdbot, then briefly Moltbot, and now it has settled on OpenClaw. If you just read the headline, you might think, okay, cool, another chatbot wrapper. I've seen 100 of these. But that is fundamentally incorrect, isn't it?
It is. Calling OpenClaw a chatbot is like calling a smartphone a pocket calculator. I mean, it's technically true that it can chat, but you are missing the entire architectural point. OpenClaw is defined as a self-hosted multi-channel gateway. It connects your messaging apps, WhatsApp, Telegram, Discord, Slack, and crucially, iMessage to action-oriented AI agents.
Action-oriented being the key phrase there. That's the real differentiator.
Precisely. It is not designed to just sit there and answer trivia or, write a haiku about a dishwasher. It is designed to be a sovereign control plane or a chief of staff. It runs on your hardware, it persists 24/7, and it has tools. It can touch your file system, it can run shell commands, it can manage your calendar. It is an employee, not just a tool.
And the hook here, the reason we are doing a deep dive today is the sheer velocity of this thing. We are talking about 150,000 GitHub stars in 72 hours.
Yeah, that is unprecedented. I don't think we've seen that since the original release of some of the major JavaScript frameworks. And it's not just software. It triggered a hardware phenomenon. It literally caused a run on Mac Minis. You go to buy a refurbished M2 right now, and good luck.
Seriously. So our mission for this deep dive is threefold. First, we are going to provide a granular, layer-by-layer technical breakdown of what it actually means to run an autonomous agent locally. We're going to look under the hood. Second, we're going to explain why the Apple Silicon Mac Mini has become the de facto standard hardware for this specific application. We're going to talk about unified memory architecture a lot.
We have to. It is the critical enabler. Without that architecture, this project probably wouldn't have anywhere near the traction it does today.
Exactly. And third, we are going to analyze the architecture, the memory constraints, the critical iMessage integration, which I know everyone wants to hear about, and because we have to, the security nightmare that comes with giving an AI root access to your life.
It is a massive double-edged sword, and we need to examine both edges very carefully before you go and install this.
Let's jump right into Section 1, Neural Signal Check. Here's why this development actually matters at a technical level.
The signal here is persistence. OpenClaw operates as a 6-layer persistence system. Most people are used to interacting with AI via a session. You open ChatGPT, you have a session, you close the tab, the session is dormant or gone. OpenClaw is an always-on loop. It creates a feeling of actual object permanence with the AI.
Walk us through these 6 layers. How is this thing actually built? Because it's not just one big Python script.
No, not at all. It's a full stack. At the very bottom, layer 1 is the gateway. This is a long-running Node.js process. Think of it as the traffic cop or the central nervous system. It manages the session state, it handles the routing of messages, and it keeps the lights on. It is not a script that runs and exits. It's a daemon. It just listens.
Okay, so that's the foundation. It's a server process. Layer 2.
Layer 2 are the adapters. And this is really clever. We all live in a highly fragmented communication world. You have WhatsApp for family, Slack for work, Discord for your gaming groups, iMessage for your friends. The adapter layer takes all these different protocols, the API for WhatsApp, the bot token for Telegram, the gateway for Discord, the socket for Slack, and it normalizes them into a singular message shape.
So it's basically a universal translator.
Exactly. To the AI agent, a message is just a message. It receives an event object. It doesn't care if that object came from a blue bubble on an iPhone or a random Discord server. It flattens the complexity of human communication protocols so the model can just focus on the actual content.
That abstraction is key for the chief of staff vibe. It doesn't matter where I yell at my assistant from, they hear me. I don't have to log into a specific portal to assign a task.
Exactly. Now, layer 3 is the agent runtime. This is the reasoning engine. This is the part that actually connects to the brain. Now, that brain can be an API like Anthropic's Claude or OpenAI, or it can be a local inference engine like a Llama running Llama 3. This layer constructs the prompt, manages the context window, which is the agent's short-term memory, and decides, do I need to just talk or do I need to do something?
And that doing something brings us to layer 4. This is the part that gets me equally excited and terrified.
Yeah, layer 4 is the tools. These are the hands of the system. This is where OpenClaw really separates itself from a standard LLM wrapper. The tools allow the agent to execute shell commands, control a browser instance using Puppeteer or Playwright, perform file system operations like reading and writing files, or even query a database.
So hypothetically, I can text my agent and say, hey, check the server logs for the last hour, grep for the word error, and email me a summary.
And it does it. It converts your natural language into a bash command, executes it via the tools layer, captures the standard output, reads it, summarizes it, and uses another tool to actually send the email. It closes the loop entirely.
That is wild to think about.
It is. Layer 5 is the surface. This is the user interaction point. It includes the control UI, which is a web dashboard running on localhost port 18789, and the macOS menu bar app if you're running on Apple hardware. It's where you configure the agent, view the logs, and manage the plugins.
And finally, layer 6.
Persistence, the heartbeat mechanism. Unlike session-based tools like Claude Code, which are reactive, it types, OpenClaw has a heartbeat loop. It wakes up on a schedule. It can check your calendar at 7 a.m. without you prompting it. It can monitor a file for changes and react. It turns the AI from a static tool into a proactive entity.
That distinction is vital. If we compare this to Claude Code or OpenAI Codex, those are fantastic tools, but they're entirely reactive. They're like a hammer. They only drive the nail when you swing them.
Right. Claude Code is optimized for a terminal-based development workflow. You're sitting there, you are driving. OpenClaw is designed for data locality and persistence. It's meant to handle your life while you are doing something else. It maintains state across multiple channels simultaneously. It remembers that you asked it to remind you to buy milk when you get near a grocery store, or that it needs to summarize your emails every morning. It has actual agency.
So we have this sophisticated software stack. But software needs a home. You can't run this on a cloud instance easily because of the cost of long-running GPUs, and you can't really run it on your laptop if you keep putting it to sleep in your backpack. And this brings us to section 2, the hardware substrate. Why the Mac Mini?
This is one of the most fascinating hardware-software alignments I've seen in my career. It's almost a perfect storm.
It really is. I mean, you can run this on Linux, you can run it on Windows via WSL, but the community has overwhelmingly converged on the Apple Silicon Mac Mini, specifically the M1 through M4 chips. Why? Is it just aesthetics?
No, it's physics. It comes down to the architecture of the chip itself. We need to do a technical deep dive into Unified Memory Architecture, or UMA.
Let's unpack UMA.
Yeah.
Because usually in a PC, you have your CPU RAM sticks those DDR4 or DDR5 sticks you plug into the motherboard, and you have your GPU with its own dedicated VRAM.
Correct. In a traditional x86 workstation, you have a discrete boundary. If you want to run a large language model locally, you need to load those model weights, which are massive files, gigabytes in size, into the GPU's VRAM. The GPU is the only thing fast enough to do the matrix multiplication required for inference. If your model is 20 gigabytes and your GPU only has 16 gigs of VRAM, you are out of luck.
Or you have to do layer offloading, right? You split it.
Right, you offload some layers to the system RAM, but then for every single token you generate, the data has to travel from the system RAM across the PCIe bus to the GPU.
Which is a massive bottleneck.
It's a huge bottleneck. It's like trying to suck a thick milkshake through a tiny coffee stir. It slows inference to an absolute crawl. You go from 50 tokens per second to maybe 2 or 3. It feels broken.
And Apple's UMA changes the physics of this problem entirely.
Completely. On an Apple Silicon chip, the CPU and the GPU access the exact same high-bandwidth memory pool. There is no copying over a PCIe bus. There is no VRAM versus system RAM distinction. If you have a 64-gigabyte Mac Mini, the GPU essentially has access to nearly all of that 64 gigs instantly.
That is huge. That means a consumer device that sits quietly on your desk can run models that previously required enterprise-grade NVIDIA clusters or multiple GPUs strapped together in a massive tower.
Exactly. It democratizes the running of dense, high-parameter models locally. But there's another factor that makes the Mac Mini the chosen one here, and that's power efficiency and its thermal profile.
Oh, this is critical for an always-on agent. If I'm running a server 24/7 in my house, I care about my electric bill.
If you are running a PC workstation with an RTX 4090 to get this kind of inference performance, that machine is idling at maybe 100 watts. Under load, it's pulling 450 watts or more.
And severely heating up your room.
And spinning fans loud enough to hear through a wall, the M4 Mac Mini, it idles at 3 to 4 watts.
That is insane. That's comparable to a Raspberry Pi.
It really is. Under load, doing heavy inference, it peaks around 40 to 45 watts. So if we do the cost analysis, the annual electricity cost to run an M4 Mac Mini 24/7 as your chief of staff is somewhere between $15 and $25. A comparable PC workstation could easily run you $150 to $200 a year in just electricity. Over 3 years, that pays for half the Mac.
Plus, the silence. We can't ignore the noise factor.
The silence is a major usability factor. The fan in the Mac Mini is basically inaudible at 1,000 RPM. If this thing is going to live in your home office or even your bedroom, you cannot have a jet engine taking off every time it processes a thought. It needs to be invisible infrastructure.
Now, I want to clarify something for the listeners. When we talk about performance here, we aren't necessarily talking about clock speed. That's a common misconception.
Right, no. In local AI, the bottleneck is almost always memory bandwidth and memory capacity. It's how fast can you move data from memory to the compute units, and how much data can you hold at once.
And this brings up the key value cache issue, the KV cache.
The KV cache, this is something people always forget when they buy hardware for local LLMs. They think, oh, the model's 14 gigabytes, I have 16 gigabytes of RAM, I'm good to go. You are not good.
Why not? Break that math down for us.
Because the model weights are just the static knowledge base. To actually reason, especially in an agentic workflow like OpenClaw, where you are feeding it context, history, previous emails, and tool outputs, you need a large context window. OpenClaw typically requires a 65K context window to be reliable in its reasoning. That context window takes up physical space in RAM. A 65K context window can occupy 4 to 8 gigabytes of RAM on top of the model weights.
So your 16 gigabyte machine is suddenly swapping to the SSD, and everything just grinds to a halt.
Precisely. You have to do the math. Model weights plus KV cache plus operating system overhead equals your actual RAM requirement. And macOS needs about 4 gigabytes just to exist comfortably.
So let's break that down in section 3. Model selection and RAM mathematics. We definitely have listeners right now looking at the Apple Store page, finger hovering over the buy button. Let's guide them through the hardware tiers so they don't buy the wrong machine for their needs.
Let's look at what I call the hierarchy of local intelligence.
Starting with the 16 gigabyte tier. Is this even usable for OpenClaw?
It is, but it's what we call the gateway machine. If you buy a 16 gigabyte Mac Mini, you are primarily going to be using it to route requests to cloud APIs. You will be using Claude Opus or GPT-4o via their external API. The local Mac handles the persistence, the tools, and the routing, but the actual heavy reasoning brain is in the cloud.
Can it run any local models at all?
It can run simple ones, Llama 3.18b maybe, but you cannot handle serious local agentic reasoning with a large context window. You will just run out of memory. If you try to load a 14b model and give it a long document to read, it will crash or stall.
Okay, moving up. The 24 gigabyte to 32 gigabyte tier, this seems to be where a lot of the community lands.
This is the starting line for real privacy. If you want the brain to actually live in your house and not send data to OpenAI, this is where you have to start.
What kind of models are we running here?
You're looking at models like Devstral-24B or Qwen3-Coder 14b. These are very capable models for coding and reasoning. But even here, you need to optimize your system. There's a specific system setting you have to change on macOS because Apple tries to protect you from yourself regarding memory allocation.
Oh, the wired memory limit tweak.
Yes. By default, macOS reserves a chunk of RAM for the system that the GPU just can't touch. If you have 24 gigs, macOS might only let you use 16 gigs for the GPU. You need to run a specific command, sudo sys to iotupo.wiredLimitMB equals 24576, or whatever your target is, to maximize the available RAM for the model. You are effectively telling the OS, I know what I'm doing, give me access to the RAM.
Then there's a quantization trick, too, for this tier, right?
Yeah, using Q80 quantization for the KV cache. This is a bit of technical wizardry baked into the underlying llama.cpp library. It compresses the memory used by that context window we talked about earlier. It effectively doubles your usable context window on Apple Silicon without really degrading the reasoning quality. It's absolutely essential for the mid-tier machines.
That's a pro tip right there for sure.
Yep.
Okay, the big leagues now. The 48 gigabyte to 64 gigabyte tier.
This is the sweet spot. This is where you stop worrying about resource management entirely and start doing real work. You can run Qwen3-Coder 32B or GLM 4.7. But the real advantage here is setting up a dual model architecture.
Dual model. Explain that workflow. How does that work in OpenClaw?
You run a heavy, smart model for complex reasoning and coding tasks, say a 32B model, and you keep a lighter, faster model, like an 8B, loaded into memory at the same time for simple routing, chatting, or summarizing small things. OpenClaw handles the switching seamlessly. You get the best of both worlds, speed for the small stuff and deep intelligence for the big tasks.
Now, we have to address a bit of a controversy in the local LLM community right now. Dense models versus mixture of experts or MOE models.
This is a fascinating debate. On paper, MOE models like Qwen3-Coder 30B look incredible. They're fast. We're talking 49 tokens per second on an M4 chip.
That sounds great, though. Who doesn't want that kind of speed?
But speed isn't everything. In agentic workflows, reliability is king. We've seen that MOE models are highly prone to infinite tool calling loops. The agent gets stuck trying to pick up a tool, drops it, picks it up again. It just loops. It gets completely confused about the system state.
And while it's looping at 39 tokens per second, it's not actually accomplishing the task. It's just failing much faster.
Exactly. The expert insight here is that dense models are heavily preferred for stability in production. Even if they run slower, say 13 to 15 tokens per second, they're just more stable. They reason through the tool use much more consistently. For a background agent that works while you sleep, reliability beats raw speed every single time. You don't care if it takes 30 seconds or 3 minutes to summarize your email overnight, as long as the summary is actually accurate.
Reliability beats raw speed. I like that. Let's move to section 4. We talked about hardware, but there is one specific software feature that makes the Mac completely mandatory for a huge chunk of the user base.
The blue bubble, iMessage.
This is the killer feature, isn't it?
It really is. For many users, especially in North America, iMessage is their primary social graph. It is how they talk to their family, their friends, their spouse. If your AI agent lives on a Linux box or a Windows server, it cannot natively touch that network. It is siloed in Telegram or Slack.
But on a Mac Mini,
OpenClaw on macOS allows the agent to interface directly with the local iMessage database. It allows the agent to respond to texts, participate in group chats, and handle media attachments natively. It turns the AI into a participant in your actual life rather than just another siloed app you have to check.
and we should mention the Blue Bubbles extension here for those looking to set this up.
Yes, the Blue Bubbles extension is highly recommended. The native integration is good, but Blue Bubbles adds a lot of stability and much better support for media attachments. It acts as a much more robust bridge between OpenClaw and iMessage.
It really highlights the sovereign control plane concept. It's integrating into your communication channels, not forcing you to use this interface.
Exactly. It meets you where you already live digitally.
All right, let's get our hands dirty here. Section 5. Installation and technical setup. Listeners, if you're driving, don't try to write this down. Check the show notes on the blog. But let's walk through the stack. What do I need to get this running?
Prerequisites first. You need macOS Ventura, so if you're 13 or newer. Sonoma or Sequoia are highly preferred for the latest MLX support from Apple. And this is critical Node.js version 22.
Node 22 is a hard requirement.
It is a hard requirement. OpenClaw relies heavily on features introduced in that specific runtime. If you're running Node 18 or 20, it will crash immediately. Also, check your system settings. The wake for network access toggle must be enabled. If your Mac goes to sleep and cuts the network card, your agent is basically lobotomized. It can't reply if it's in a coma.
Good point. What about the installation stack itself?
You start with Homebrew, standard package manager stuff, then Xcode tools. Run Xcode select -- install in the terminal. Beginners often miss this step.
Why is that Xcode step critical?
Because OpenClaw needs to compile native bindings for the database and the system events. If you don't have the Xcode command line tools installed, the npm install command will just fail with a bunch of scary red error messages about node build failures.
Got it. And installing the OpenClaw CLI itself?
The simplest way is npm install -g OpenClaw at latest. Or use the curl script if you're feeling adventurous and trust the internet.
Once it's installed, you have to run the onboarding wizard.
Right, you type OpenClaw onboard -- install daemon. Do not forget the install daemon flag.
Why is that flag so important for a stable setup?
Because without it, OpenClaw is just a process running in your active terminal window. If you close that terminal window or log out, the agent dies. The daemon flag registers OpenClaw as a launched background service on macOS. It ensures the agent auto-starts when the Mac reboots and stays running in the background, entirely independent of your UI session. It makes it actual infrastructure.
Now, accessing this thing, we are running it on a Mac Mini in the closet. We aren't plugging a monitor into it.
Right, it's a headless server setup.
So how do we talk to the UI securely? Just set up port forwarding on the router.
No. Please, absolutely do not port forward this to the open internet. We will get to why in the security section, but just don't do it. You are exposing a root-capable agent to the web. The recommended architecture for remote access is Tailscale.
We love Tailscale on this show.
It creates a private tailnet, and OpenClaw has built-in integration for it. You just set gateway.tailscale.mode to serve in the config. This allows you to access your agent's dashboard and API from your phone or laptop anywhere in the world over an encrypted tunnel without exposing a single port to the public web. It is infinitely safer.
And one advanced tip for the security conscious regarding API keys.
Secret management. Yes, do not store your Anthropic or OpenAI API keys in plain text in a config file. That is terrible practice. OpenClaw supports the Bitwarden CLI. You can use Brewgit to inject secrets at runtime. It keeps your keys encrypted at rest in your vault.
That is a pro move. Okay, we have to go there. Section 6, security vulnerabilities. We built this amazing, powerful agent. We've given it shell access. We've connected it to our iMessage.
And now we have to talk about Clawjacked and Clawhavoc.
Yeah, neural signal check. Security. This is the scary part. The same features that make OpenClaw so powerful, the persistence, the shell access, the tools, make it a massive, massive risk.
It's the classic security trade-off, right? Utility versus security. In the enterprise world, we call this shadow AI, but in your home network, it's just shadow risk.
Let's talk about the Clawjacked exploit. This was a nasty one.
It was a critical flaw in the WebSocket handling. Here's the technical detail. OpenClaw's gateway runs a WebSocket server. To make setup easy for users, the developers relax security for connections coming from localhost.
Because the logic is, if it's coming from localhost, it's you, right?
That's the naive assumption. But a malicious website you visit in your web browser also runs code on your local machine via JavaScript. So the attack vector was a simple drive-by. You visit a site, maybe a fake news site or a pirated movie site, and that site's JavaScript opens a WebSocket connection silently to localhost port 18789.
And because Gateway saw it, oh, it's local, it must be safe.
It allowed the script to brute force the password because there was zero rate limiting on local host requests. Once it guessed the password, or if there was no password set, which was unfortunately the default in early versions, it registered a new trusted device without asking the user for confirmation.
And once it's a trusted device, what can it do?
Full remote code execution, RCE. The attacker completely controls the agent. They can read your files, exfiltrate your SSH keys, install malware, or use your machine as a botnet node. It was a total compromise of the host machine.
That has been patched, right?
It has, yeah. In version 2026.2.25, they added strict rate limiting and mandatory physical confirmation for new devices, but it really highlights the fragility of these autonomous systems.
Then there's Clawhavoc. This wasn't a code bug in the gateway. This was a supply chain attack.
This involved the ClawHub marketplace. Just like the App Store or NPM, people upload skills for OpenClaw. Researchers found over 341 skills that were entirely malicious.
What were they actually doing?
Masquerading as crypto bots, or productivity tools, or enhanced search extensions, but they were actually delivery mechanisms for Atomic Macro Stealer, or AMOS.
AMOS is nasty. It grabs everything.
It is. The mechanism was pure social engineering via the terminal. You install the skill. The skill says, hey, to run this feature, I need admin permissions. Please enter your system password. It pops up a fake CLI dialog. You type your password.
And it's game over.
It quietly exfiltrates your macOS keychain data, your browser passwords, your crypto wallet seeds, everything.
So how do we harden this setup? What are the actual strategies to protect ourselves?
First, network isolation. Bind the gateway strictly to 127.0.0.1. Do not bind to 0.0.0 unless you really know what you are doing with your firewall.
Second strategy.
Approval gates. You go into the config and set exec.ask2 on. This means the agent must ask you for explicit permission before running any shell command. It slows things down, but it stops the agent from wiping your drive because it hallucinated that it was a good idea.
And what about sandbox mode?
Yes, definitely utilize the version 2026.2.25 sandbox mode. It restricts the agent to read-only access for most of the system file tree. It limits the blast radius if it does go rogue.
And finally, identity separation, which we touched on earlier.
Ideally, you run this on a dedicated machine. Do not run OpenClaw on your primary work laptop that has your company's VPN keys and your personal tax returns on the desktop. Put it on that Mac Mini in the closet. If it gets burned, you wipe the Mini. You don't lose your digital life. Treat it as a semi-untrusted device at all times.
Wise words. Let's move to something a bit lighter. Section 7, customization, the soul of the machine.
This is where it gets really fun for developers. The directory structure includes a folder at /.openclaw/workspace.
And in there, there's a specific file called soll.md.
Right, this file is the persistent system prompt. It is loaded into context at the start of every single conversation. It defines the tone, the ethics, and the overarching personality of your agent.
So if I want my agent to be, I don't know, a snarky British butler, I just put that directive in soll.md.
Exactly. Or if you want it to be a rigorous, highly concise technical writer, you define it there. It sets the baseline behavior. It's essentially where you inject the vibe into the local model.
And for memory, there's a memory.md file too, right?
That's for flat file preferences, like user likes coffee or user works primarily in Python. But for the heavy lifting of long-term memory, OpenClaw integrates natively with vector databases like ChromaDB.
Explain why a vector DB is better than just grepping a text file.
It comes down to semantic search. If you search a standard text file for the word dog, you only find the exact string dog. If you search a vector DD for canine companion, it understands the semantic meaning and connects it to dog. It allows the agent to recall information based on abstract concepts, not just exact keyword matches. It makes the memory feel much more organic and intelligent. It can say, oh, this reminds me of that architecture project you mentioned last week, even if you didn't use the exact same words this time.
Section 8, economic and enterprise implications. We talked about the power cost earlier, but let's look at the broader total cost of ownership, the TCO.
If you buy a $599 base Mac Mini versus paying $20 a month for ChatGPT Plus and maybe another $20 for Claude Pro, the break-even point is roughly 2 to 3 years.
That seems like a pretty long time to see a return on investment.
It is if you look at it purely as a one-to-one chatbot replacement, but the utility is vastly different. You are paying for the iMessage integration, the local file processing, the absolute privacy of running local weights. That utility value is hard to quantify on a spreadsheet, but for many power users, it's worth the upfront cost immediately. You own the intelligence infrastructure.
And on the flip side of that, the enterprise risk. Shadow AI creeping into the corporate network.
This is what's keeping CISOs up at night across the industry. Imagine a well-meaning employee deploying OpenClaw on a corporate network to automate their Jira tickets or review pull requests automatically.
Honestly, it sounds highly efficient.
It is efficient, but from a security standpoint, it's a nightmare. You have an unmanaged, autonomous agent with shell access, potentially listening to internal communications, with absolutely no governance tools. There's no role-based access control or RBAC, no audit logs that IT can even see. It is a massive vulnerability hole.
It's basically the bring your own device problem on steroids. Bring your own agent.
Bring your own autonomous root access agent. It's terrifying for IT security teams. Companies are going to have to develop policies and detection methods for this very, very quickly.
We've covered a lot of ground today. Let's head to the outro and wrap this deep dive up.
We really have. We've gone from the core chip architecture to the software stack down to the dark web exploits targeting it.
To summarize for everyone, the Mac Mini plus OpenClaw combination is a genuine glimpse into sovereign AI. It empowers you, the user, to actually own the intelligence, to integrate it smoothly into your daily flow via iMessage, and to run it highly efficiently.
Right. But it requires a rigorous security posture. You cannot just install this, run the daemon, and forget it. You are essentially becoming the system administrator of a very powerful, potentially dangerous tool.
Which brings us to our final provocative thought for the listener, something to mull over.
As these local agents become more capable and we freely grant them chief of staff privileges, we are essentially creating non-human identities with admin access to our lives.
Right. And where does the liability fall?
Exactly. If your agent negotiates a contract via email while you are asleep, or if it deletes a critical shared database file because it misunderstood a simple cleanup command, who is legally liable? At what point does the tool become an autonomous legal entity? If my agent accidentally hacks your agent because of a weird tool loop, did I hack you?
That is absolutely something to chew on.
It's the wild frontier of digital law and ethics, and we are walking right into it, completely blind.
Thank you so much for listening to Neural Intel. We want to know, have you set up a local agent? Did you go for the 32 gigabyte or 64 gigabyte Mac Mini, or did you brave the 16 gigabyte tier?
And did you secure it properly? Please tell us you secured it properly and aren't running it on 0.0 or near ago. Let us know in the comments.
Don't forget to check the blog at neuralintel.org for the config files and architecture diagrams. And please subscribe to the show.
Until next time, keep your signals clear.
This has been the Neural Signal Check, signing off.